This is section 2.5, transformations of functions. The first thing we're going to do is we're going to learn to identify several basic graphs. So we're going to talk about a basic constant function, a basic identity function, a basic absolute value function, and so on. And then once we have these, which I call your library of graphs, then we're going to start to talk about how we can tell where these graphs get moved based on various variations in their formulas. So we'll be able to look at a formula and say, okay, well, that's that kind of graph, but it's going to be moved up 3 and left 2. So we'll be able to have a good idea from looking at the equation what our general graph is going to look like. Okay, so the first of these is basically f of x is equal to a number. This is called the constant function. And we'll look more, I have number written here, but it'll be f of x is equal to k, where k is some number. Now this number is going to be your y-intercept. And this is going to be a horizontal line. This is basically the equivalent of y equals b. When we first started talking about horizontal lines, we know that f of x is like y, but it means a little bit more. With y, we may or may not have a function. If you see f of x, you definitely have a function. And you can remember that this is going to be a horizontal line instead of a vertical line, because if it's a vertical line, it does not pass a vertical line test and it is not a function. So let's just say that, because I need to do a general example graph here, let's say that we have f of x is equal to 2. Then what that line is going to look like, it's going to be a horizontal line with a y-intercept of 2, which is right there. And so our horizontal line will look something like this. Okay. So that is one example of a constant function. Of course, it just depends on what this number is, where your line goes, but it's always a horizontal line through that particular number. Okay, so let's look at f of x is equal to x. What this is saying is if you plug in x, you get x. So these are identical. This is the identity function. What this line looks like is it is going to be a diagonal line that cuts these two quadrants in half. Because think about plugging in some numbers here. If x is 1, y is 1. If x is 2, y is 2. If x is 0, y is 0. You can see what's happening there. It's the identity. So this line ends up being a diagonal line through the origin with slope of 1. Okay, and if you think of it in this form, y equals mx plus b, the number in front of our x is a 1, so our slope is 1, and the number we're adding to it should be our y-intercept, since I can always do a plus 0 here without numerically or algebraically changing the value of the equation. That says my y-intercept is 0. Okay, let's look at this one. F of x is equal to the absolute value of x. We call this one the absolute value function. Okay, and you're going to see a definite correlation between this graph and this graph. Remember, this says you take whatever is here, you plug it in, and then you make sure that you get a positive answer out of that. So if I plug in positive 4, I get positive 4. But if I plug in negative 4, I get positive 4. So whatever we plug in becomes positive. If it starts off positive, it stays positive. So let's see. If I plug in 0, the absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of negative 1 is 1. The absolute value of 2 is 2. The absolute value of negative 2 is 2. You can see that in quadrant 1, our graph is identical to the identity function above it. And that's because when you plug in these numbers and you go to make them positive, you didn't have to change anything because they were already positive. But what did change is over here. Whereas here I plugged in a negative number and I got a negative answer. What this does is it basically takes this and flips it up to here. It makes all of these numbers that were negative positive. So I basically get a giant V shape like this, okay? This is the only one of our graphs that comes to the point. Everything else we do is some sort of curve or straight line. Nothing else comes to a very definite point. Okay, so our next one, f of x is equal to x squared. This is called the standard quadratic function. Okay, because in order to be a quadratic, the most basic requirement is that you have a square term in it. And nothing raised to a higher exponent than 2. So this meets the minimum standard for being a quadratic function. Now, this is one we deal with a whole lot, so I'm going to do a t-chart to help make sure that you see where all of this is coming from. So let's say my x is here, my f of x is here. And let's plug in some negative numbers, -2, -1, 0, 1, and 2. These 5 points should be enough to get a good graph. If I take -2 and I square it, that's the equivalent of -2 inside parentheses squared. So this is a positive 4. So I have -2, positive 4. Okay. If I plug in -1, that's the same as -1 inside parentheses squared, which gives me positive 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. You can see how this one, kind of like the absolute value before, took stuff that was negative and made it positive. This is all kind of ties in later on in chapter 2. But for right now, we're going to connect these and as smooth a curve as we possibly can. Make sure it's curved at the bottom and it does not come to a definite point. If we were doing online, we were not doing online tests. If we were doing paper tests, I would just expect you to draw me something that's curved. And if, for example, you drew it and it looked pointed to you, I would tell you to draw an arrow to it and tell me that it's not pointed, okay? Because I don't grade you on your artistic ability, I grade you on your math. Okay, now we're going to be using this graph quite a bit later, and I want to show you what I've done. I have taken some tracing paper, and basically I have just traced it onto here because we're going to be moving this around. So I want you to see where this sheet comes from, and then I do that with a couple of other graphs as we go along, the ones that we're going to be using more of later. Okay, so let's look at f of x is equal to the square root of x. This is the square root function. Now, one thing we have to be aware of here is that we have a restricted domain. We are not allowed to take square roots of negative numbers. So that means I cannot plug in -1 or -2, anything over here. It just doesn't exist. The smallest number I'm allowed to plug in is 0. So 0. The square root of 0 is 0. So I have that point right there. 1. The square root of 1 is 1. Now I could plug in 2. The square root of 2 is about 1.4. The square root of 3 is about 1.7. But I'm going to go back up all the way up to 4 because the square root of 4 is 2 and it gives me another nice little number to deal with. Okay. One thing you might notice is that these values are the reverse of these. well, of course, 0 and 0 flipping doesn't make much difference. 0 and 1 didn't flip. But here the 4 and the 2 flipped. And if I kept going, if I plugged in 3 and got 9, I could plug in 9 here and get 3. Basically, these two functions kind of undo each other, and that becomes important later as well. But for right now, this doesn't exist. I cannot plug in negative numbers. And if I'm plugging in positive numbers, I'm never going to get a negative answer. This graph starts at 0, 0, and it moves up like this. The other thing you might notice, this is my graph of x squared. If you take this and you turn it on its side and graph only the top part, you've got the square root function. Okay? F of x is equal to x cubed. This is the standard cubic function. Okay, in order to be a cubic function, you have to have at minimum an x cubed. You can't have an exponent larger than 3. You can have every exponent below 3, so you can have a square, first power, and everything else in there. But the minimum requirement is to have an x cubed. Now what I'm going to do here is I'm going to, again, plug in some values for x, and see what I get for my y, or f of x. Okay, so let's just say I'm going to start at, let's start at -3. And I'm putting those in parentheses right now because, so I didn't have to remember to do this, I guess. I've got no other good reason. So -1, 0, 1, 2, and 3. And let's see what we're looking at. If I take -3 inside parentheses and then cube it, that's -3 times -3 times -3, which is -27, which of course does not fit on my graph. And that's okay though. I'm going to use this to direct, to get an idea of what the graph looks like anyway. If I take -2 and cube it, I get -8, which is also off of this grid. If I take -1 and cube it, I get -1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. Okay, let me just plot the ones here that I can plot. I have 0, 0. I have 1, 1. And I have -1, -1. These are the only ones that fit on my graph. Now, if I'm not careful, these happen to line up in a straight line. But this is not my whole graph, okay? If I draw this as a straight line, then that would say that if I plug in 2, I should get 2, and I definitely don't. If I plug in 2, I get 8, which is way up here. If I plug in -2, I get -8, which is way down here. This graph looks something like this. This looks like a curve right here, and then it's like the curve turns upside down. Okay, if you ever took pre-cal or calculus, you may have learned concave up and concave down. That's all this is, but if you have never heard of that, don't worry about it. Now, what I find interesting is a third power can give you negative answers, whereas a second power cannot. If you look at this, this is our x squared graph, and you can see that this positive side has kind of the same shape. It's a little bit different, but it's kind of the same. And then this side is sort of like flipped upside down. Okay? All right, one more of our basic functions, and then we'll go on to transformations. Okay, so I have f of x is equal to the cube root of x. This is our cube root function. Okay? And a cube root undoes a cube in the same way that a square root undoes a square. So we're going to see a lot of x and y switching around as well, like we did on the other two. So let's just, let's plug in some numbers here. So I'm just going to pick some random numbers. Let's say, what's the cube root of 1? Well, that's 1. So that's 1, 1. The cube root of 0 is 0. Okay. Well, the cube root of -1 is -1. So right now I have the same 3 points I had for my cube function. But again, these line up in a straight line, but that's not my graph. I definitely need more information. Well, taking the cube root of 2 is going to give me some decimal, so I'm going to go up until what would I find next? Well, if I take the cube root of 8, that's 2. Well, if I go out to an imaginary 8, which is way out here, then I'm up at 2. And the same thing happens at -8 and 2. Okay, so this curve, notice this side seems very similar to the square root function. It's a little bit flatter because it's a cube root, not a square root. But then since we are allowed to take cube roots of negative numbers, unlike with square roots, this side also exists. Okay, and it looks a lot like our cube root function turned on its side. Okay, in the next part, we'll start moving these things around.